Hello, everyone. Welcome to our presentation. The presentation that we are going to give today is entitled by an overview of gradient descent for machine learning. We are performing this presentation for the completion of the course CAC 6240, Mathematics and Theory of Machine Learning. This is a group presentation, and the team, myself is named Ahsan. I'm a PhD student here at Tennessee Tech. The team includes John, who is also a PhD student in the Department of Civil Engineering. Then we have Ryan, who is a PhD student in the Department of Computer Science. And we have Jonathan, who is a master's student in the Department of Computer Science as well. Before we begin on to the presentation about the gradient descent and machine learning, let's discuss about the realm of intelligence. Intelligence, in my opinion, is the ability to process information in a way that it can provide future information. So to start off, AI, in my opinion, is what focuses on building algorithms that can do that I've just described. Machine learning, which is a subset of artificial intelligence, which provides us the ability to learn without we program anything explicitly, which is a traditional programming that we know as of now. Deep learning is also a subset of machine learning, and with deep learning, we leverage that to extract patterns from the data set using neural networks or different foundational blocks that we will be describing in this presentation. Now that we have described now that we have described the realm of intelligence, let's start off by knowing what we know about perceptron. Perceptron, or a neuron, is a building block of a neural network. It consists of a set of inputs that we label here from x1 until xm. M could be any number in our experimentation. All the inputs are associated with the weights, and then in this particular example, we provide that with a summation function. And then with help of activation function G here, we will get an output. By that, we will propagate a piece of information feeding to input, and then it will lead towards the output. This right here is the expression or mathematical expression that we could derive from this figure. So Y here is our output, and then with the activation function, this is exactly what we are doing in this example. However, this is not perfectly correct. We will add a bias in this network, which will allow activation function to shift from left to right in order to provide us with better results. And with that inclusion, we add that in our mathematical formula here with B plus here. And we will add the bias after we will perform the summation in this case. And activation function here is all about, there are many activation functions that we could incorporate in our mathematical expression that we have shared before. In this example right here, we have introduced sigmoid activation function that takes any real number as input on the x-axis, and it transforms the real number into a scalar output between 0 and 1 as per the bound. And in here we have collapsed both x and y in terms of vectors respectively. And the reason why we do that, we are wanting to take a next step from the foundational block. We could get rid of all those summation function in a way. We will draw the schema here. So we have all the inputs on the left side, and then we will pass the direction towards the activation function. This is what we can derive or deduce the network that we have shared before. And we could add another perceptron to the network, and by that we can add as many hidden layers as we can, and the description of hidden layer will be described later. But all it's doing is it will be doing its own task with some activation functions. With that in mind, let's discuss a case study for MNIST dataset. And for MNIST dataset, it is a handwritten dataset for so many users. In here, every image in here is, if we can consider that as 28 by 28 pixel, if we multiply both of them together, that would become 784. So we have got 784 inputs for one picture. We could describe as per this matrix, and from there we can simply collapse that in a vector which has got 784 inputs. So we have got those set up here, and then with some networks we will be feeding the knowledge in this schema right here. So for this case, let's say we want to predict the digit 5. For the first time the network is trained, it is likely that we will not be getting the network telling us, okay, you are feeding the input 5 as prediction. With weights being adjusted over the period of time, we will be able to provide a better prediction from this network. My friend John now will be describing how the weights are adjusted, and he will take it on from here.
Thank you, Ahsan. As he was saying, these neural networks are learning without being explicitly programmed, and they're doing this through these weights. So let's talk about how we can learn these weights. So far, we've just been pulling them out of the ether from somewhere. So pay attention to this sum here, as this form will be used a little bit later. Actually, right now. So we have this form of the sum that we're looking at here, particularly this sum. Well, there's a parallel that we have to that in typical statistics, which is the simple linear model with beta weights. So you notice that we have our weights here that are the parallel, the beta with the W, and then our inputs are numbered exactly the same, and this goes on through a sum of M. We also have a constant here just to show some of that as well. So in order to learn the best weights that we can get, we want to optimize the error that we're making. Our gradient descent is descending down error is the goal. So we need a way to summarize the error that we make at a particular set of weights at several locations and collapse that into a single number. That's going to be what we're going to call a cost function. So let's take a look at an example of that. So just for simplicity's sake, so they can fit on the slides, let's look at a first order linear model. So we only have 2 beta weights that we're learning here. So I have some data here, and we have fit a line through it, and any of you who have done statistics before are going to say that's not the best fit line that you can draw through that. It is intentionally not the best fit line that we can draw. This is just some starting. We might randomize our weights. That might be how we get our starting weights, and we might end up with something like this. So you see where I have marked the residual here, the difference between what that model predicts versus what the data actually say. If we sum up all of those, the absolute values of those, and the mean absolute error, we're going to get 6.73 in this case. If we do the ordinary least squares algorithm, guaranteed to be optimal in this instance, then we actually end up with 3.505. Remember that number for later. You're going to need it. So there are, in different machine learning instances, we might be solving a classification problem or a regression. There are different loss functions that we might use. And when I say loss versus cost, what I mean is that the loss is really this term here, and the cost is taking the average of that or taking the sum of that over all of the data that we are training against. So we might have the mean absolute error. That's the one that I've been talking about. That's the one the details examples are. Were we to square those residuals, we would get mean squared error. And if we were in classification, we might use hinge loss or binary cross entropy. So then I've been talking about we're going to update weights. How do we actually update weights? The cost function tells us how far off we are, how much error we made. And so our goal to learn a system is how can we be less far off the next time around? So this is where the meat of that gradient descent algorithm comes in. We evaluate the gradient of the cost function where we are at a given step and observe the direction which allows us to proceed most quickly towards minimizing that cost function, i.e. minimizing the error. So we have this row vector of all the derivatives of the entire function, of the cost function, with respect to each variable that we're looking at. So in the example that we're looking at here, we only have a 2-term gradient that we're going to be dealing with. So we will actually adjust the weights in the opposite direction of the gradient, since that gradient is technically the direction of steepest ascent, because that would be increasing error if we went in the direction of the gradient. We want to go the exact reverse direction. So we evaluate that gradient. Going back to the example that I have here, where we started at before, we have these beta weights that we started with on our first iteration. And if we find the gradient of the cost function there, then we actually have -0.6 and -50.724. So this is much, much larger. So that says we need to make a much larger change in beta 1. So let's go ahead and introduce the concept of a learning rate, this alpha here, because if we made the change to -50, that slope is going to be through the roof. So we only want to adjust it by a small amount in the correct direction. So let's choose a small learning rate, say 1,000th. So then we multiply that through, and we add these two matrices together to get our new updated weights. And you see that green line has shot up off the page there. And our sum of residuals is now very, very high, 34.18. And it actually gets much higher than that, all the way up to 1 to the times 10 to the 18th, before eventually it begins to converge back down to a reasonable number again. So you would do a convergence analysis like this to determine how many iterations of this algorithm to do. So after 100 iterations, we've now converged to a reasonable result. If you look at the best fit line, that looks pretty good. Let's compare that with the ordinary least squares. So you see that our first beta weight, the constant, is very different. Our slope is not all that different, but our sum of residuals, that mean absolute error that we're optimizing, they are very, very similar. Gradient descent isn't necessarily able to find the most optimal solution, but it will find a reasonably optimal solution. And with that, I will turn it over to Ryan, who will explain more.
All right, thanks, John. So we've so far talked about the problem and the theory behind calculating the gradient and applying it in terms of backpropagation to our machine learning weights that we have. And so we're ready to apply this right to real world the MNIST digits. But we have some major decisions to make because it's not that easy, right? So for smooth, well-behaved m-dimensional surfaces, we can do that. It's pretty easy. If the surface is convex like this one, there's going to be one global minima that'll be easy to find, so we'll converge on top of it. But when we have as many dimensions as we have in a machine learning problem, the surface is going to be irregular. There'll be multiple candidates for local minima. There may be saddle points that exist that prevent convergence from happening. And so we have some tunables in order to help us out. And so one of the big decisions that we have in implementing gradient descent on a machine learning problem is this batch versus stochastic gradient descent question. So batch gradient descent is where you calculate your gradient vector and do backpropagation, after one pass through the training data, which can take a while because it's a lot of information that's sort of been learned so far. And so with stochastic gradient descent, you actually do that every single example that you see. And so you can do stochastic gradient descent in a live way, right, on every new input. And so then if you want to do something between the two, right, mini batch allows you to kind of customize your batch size. So maybe you might update and backpropagate, update your weights every 500 samples, even though you might have a training set of 2,000 or more samples. So that's one thing you can tune. Another thing you can tune that we'll talk about here in a second is learning rate. Essentially, this is how much you move your weights at every step. Of course, the higher the learning rate, the more likely you are to overshoot your intended destination, and the lower the learning rate, you might get stuck in local minima that you don't want to be at, right? So there might be a better solution that's close by. And then finally, momentum is a concept where if you have gradient vectors that change direction quite often, you might try to remember previous directions and implement that somehow to prevent your gradient vector from shifting quite a bit. And so, thinking about learning rate, if we have, this is an example, this is our curve here, and so we can see pretty quickly, right, that what we want to do is have this general slope down, and we want to converge on this local minima right here. And so but we also have, these two little valleys that exist that are also local minima, and we don't want to get hung up. And so, adjusting your learning rate to sort of move at each step past these far enough, you'll end up converging on this, which is a good solution. On the other hand, right, if your learning rate is too high, you might, plow past this, and there might be other local minima up here, but that would be a worse solution. We don't want that to happen. And then, stochastic gradient descent is particularly bad at navigating ravines. So this is a contour plot here, where, this is the lowest spot of this surface. And, the update vector can change direction. So if we're coming at it from this direction, each of the gradients will be perpendicular to the normal to the contour line. And we have a lot of jumping across that we see here. And so by remembering the previous direction, instead of having a normal to the contour line, if you remember that you were proceeding, in this kind of direction, you can minimize the wrong answer. You can take into account your previous direction to help end up where you really want to go. And so, of course, there are many enhancements that are not just momentum or learning rate adjustments. These are a sampling of them. I'm not going to go into them, the interest of time, but sometimes you might choose to use momentum, and maybe try to figure out where you're anticipating your weights to end up to help understand which momentum you want to use. You may also decide that you want to adjust your learning rate based on the slope of a particular dimension, and so you might have different learning rates for different dimensions in some of these. But I really wanted to show that this is an example of a saddle point right here on a surface. Some techniques do converge quite fast. This is the local minima that we're trying to hit, and some techniques may get hung up in certain areas. And then finally, the question is, well, what if we don't use gradient descent? What if we use some other alternative like simulated annealing, right? And so finding an approximate global minimum, which is what simulated annealing can do, could work, right? But those algorithms typically suffer from long run times. And then at the end of the day, right, do you really want the most perfect global minimum? Maybe the local minima are good enough. If you have so like the cost function, right, is really a measure of certainty in an answer. And if we are 100% certain after seeing a certain set of training data that we're going to get the right answer on any new information that comes along, we might be overfitting. And so maybe finding local minima that's a good approximation is really good enough. And so the other advantage to gradient descent is that it's pretty easy to understand. And there's been a lot of research that's gone into optimizing it so that it converges pretty quickly and accurately.
Thanks, Ryan. So basically what we're going to do from here is I set up a Python code to do a parametric study of this MNIST data set, and downloaded the data sets as a binary file, and we can read them in and actually look at how some of the other parameters like decay and Nesterov, epochs, batch size, hidden dimensions, things like that will actually affect the way that we have testing and training accuracy from a model that we build and using gradient descent. And so the learning rate, kind of like what Ryan said, was basically like the magnitude by which the weights are updated. This is kind of like multiplying the gradient to move a ball down a hill, per se, if you want to think of it in sort of a physical way. The decay is actually more like a shrinking of the learning rate over time. And it's a multiplicative factor as a function of the iterations or the epochs that actually kind of slows down the ball slightly so you're not moving so far. Momentum, like he said, you use the previous motion to actually kind of model real physics in the real world. And so when you have a ball, again, rolling down a hill, it just immediately cut to the left. It actually uses the momentum of the ball to go in a different direction. That's actually, you combine the two vectors together, right? And then so the Nesterov sort of accelerated gradient, the NAG, it does a prediction of the next iteration's parameters and actually adds the two vectors together to get an actual calculated gradient, and then sums the two, which is pretty similar to the way that momentum works. but it works a little bit differently. And I won't get into the math of it just for interest of time. And then he already mentioned the epochs. It goes through how many times it goes through the entire data set. The batch size is how many samples that you actually take per look at your data set. The hidden dimension size is how many neurons you actually put in that perception layer. And then the number of layers just is how many you get between the input and the output. And both the hidden dimension size and number of layers will directly affect the parameters, the weights that are available for your model. So the meat of this particular project that I set up was I used 7 for loops, right, and ran a sub-process on this MLP MNIST.py sort of single run. And I was looping through 10 ranges of values for each one of these. And so ultimately that was gonna run our model 2 million times. But I tried to do it a little bit more systematically. And so we got about 2,000 different runs with a bunch of different points and values. And this code is actually available on GitHub if you want to go look at it. And so basically what we want to look at is we want to look at the way that some of these parameters are affecting the training accuracy. And so the general rule of thumb is that when the learning rate is too high, when it's close to 1, a lot of times what happens is it just gets really jagged and it doesn't converge to a particular value. Or when the learning rate is too low, like 0, it actually gets very stagnant and doesn't really move at all. And so in between 0 and 1 is where you kind of want that to be, but 0.001 is a pretty good value, and this has been confirmed by some of the other articles and things that we found, and is also, as it turns out, consistent with the data that we collected. And so based on the data that we collected, if we look at graph A here, there's this little cluster where I ran a lot of different tests when the learning rate was equal to 0, and the only thing that it did was actually just do random guessing based on the initial weights that it initialized the model to. And so we can see that the accuracy was not very good at all. But while keeping the other parameters constant, and we actually started increasing the value of the learning rate, we actually kind of start converging to where at 0.004, we actually get the best sort of accuracy there. And then at graph B, I also did an extreme case where I actually increased it up to actually a value of 10, and we can see the accuracy actually starts plummeting again, which is still consistent with our data. We can also look at the variation between learning rate and momentum. And so this little gray cluster down here actually represents where the learning rate was 0, and we still get that really bad accuracy. And the line of purple dots on the bottom represents the accuracy where the learning rate was the same, that 0.001, and the momentum was increasing in a extreme case. The colorful dots here in the middle represent where the momentum was relatively constant between 0.9 and 1, but the learning rate was changing. And then the purple dots up here is actually where we want to be, is this general trend where the learning rate was the 0.001 and the momentum was varying between 0 and 1. And so this is actually where we wanted to be, which is still consistent with the articles and our data. And this is actually just a stripped down version of the same thing, modeling the momentum trend as we left the learning rate constant. And so one of the last things that we did was we actually did a principal component analysis and actually realized that the learning rate and the momentum here explained the most variance for our data. And as a result, it became the 2 most influential parameters to optimize the accuracy for our experiments and for our context. And so through this practical analysis of the MNIST data set, we actually validated that the results that we extracted were consistent with the general rules of thumb that we found in the field and also posted in different articles, and that our intuition about accuracy decreasing as learning rate and momentum exceeded the recommended values was not only correct, but also makes sense from a logical and physical point of view, and as well as mathematically. And finally, performing the PCA not only provides us with further evidence to support the benefits of optimizing learning rate and momentum for similar machine learning problems. So with that, thank you.